Okay, hello everyone. Today I'd like to present the Monte Carlo dose calculations. As you know that most of the Monte Carlo simulations adapted the dose calculation algorithms based upon the cavity theory, which is we learn a lot from this class. So today's talk about the Monte Carlo dose calculations, most likely reference book is actually our textbook written by the ethics or Andrea. Also, I actually the references about the calculations from the various Monte Carlo manual. So overview about this talk, I'm going to talk about the basic dosimetries and including the fundamental principle. I'm also talk about some intermediate dosimetries, including delta rays calculations. Further down, I can talk about the advanced dosimetries, which can implement the Monte Carlo simulations calculations. I'd like to introduce the perturbation factors, and further down, I'm going to introduce about some example of the Monte Carlo simulations, and lastly, I'm going to briefly talk about the issues and suggested solutions for the Monte Carlo treatment planning systems. As you know that the textbook informations, we know very well about the conversion factor between the mediums and the detectors, basically described by the conversion factors. So those ratio in between the medium and detectors is described by the conversion factors as a function of the radiation beam qualities. So basically those in the medium and under the charged particle equilibriums, and for the charged particle cases, the fluence of the particles times the stopping powers integrated over the given energy range, they're going to be equal to those in the medium. And for the photon cases, and instead of using the stopping power, we have to put into the mass energy absorption coefficient of the material integrate over the energy range under the partial charge particle equilibrium, or in other words, the transient charge particle equilibrium. So this is well known from the very simple cavity theory, which is a gray cavity theory, VG theory, which is under the assumption of the cavity size is very small enough, is not to perturb the fluence of the particle, and secondly, the whole energy deposition is solely done by this charged particle trap, and photon interaction is going to be negligible. So in that case, is that these conversion factors between medium and detectors is definitely proportional to the stopping power ratio between medium detector, which can be written by the fluence times the stopping power in the medium over the fluence times the stopping power in the detector. Further down, we know that we want to implement to take into account the delta ray effect, which once the delta ray equilibrium the breakdown, then we have to introduce the restricted power stopping power instead of the unrestricted stopping power, which is called the Spencer-Attucks cavity theories, which is written here. So we can split out the delta ray cutoff energy integration region between delta over to the E maximum, or 0 to the delta cutoff energy region of the medium over detector range. So under the assumptions, of course, it required the BT cavity assumption plus the charged particle equilibrium is required. Well, this is actually we learned from the class. So here's an example, the great example of the delta effect, which in other words is the density or the polarization effect, which shows that the relative ratio of the stopping power to water in this case is as a function of the electron kinetic energies. Because of stopping power is a function of part of the delta, and this delta actually showing here is a negative component inside the stopping power. So definitely the energy is increasing. This delta cutoff energy is also increasing. That's why we have difference is going to be getting larger and larger as increasing the beam energy. The second one is the photon cases under the charged particle equilibrium. I mentioned that in the photon cases, the cavity and going to be large enough compared to the range of the CSDA, and we can apply the mass energy absorption coefficient inside of the integration part instead of the stopping power. So the conversion factor is equal to the ratio of the mass energy absorption coefficient between the medium and detector. Here, the energy dependence of the fluence between the electron and the photon. Electron case is showing that the left-hand side, and the right-hand side is showing the photon cases. So in that cases, as you see that the difference between the two electron and the photon, and in terms of the depth, as you see that the charged particle cases, the electron is going to be very different fluence dependence. However, the photon showing that the very the similar pattern of the fluence, the distributions, even different depth, and the energy dependence is going to be a similar way. On the other example of the depth dependence of stopping power for the electron and the photon comparison between here, the left side and the right side for the photon and the electron. Spencer adding stopping power the ratio between water to air. So as you see that the depth dependence of the given energy is kind of varies. However, the tissue phantom ratio as a function of the depth water for the photon cases is very kind of consistent and very independent of the depths of the water. So in realities, we cannot assume the detector size is small enough. So in order to neglecting the fluence perturbative effect. So instead of this kind of ideal assumption, we have to apply some minor corrections. Those corrections should be, as I said, minor, small, but depends upon a lot of sources, which most likely coming from detector side. So we call it the influence of the detector perturbation factor. So these factors going to be the depends upon detector volume effect, or material dependence, or intrinsic some differences between the medium or detectors, or purely coming from detector type. So what kind of electrode node it used, and or stem structure, stem material, or central rod location, central rod size, and so on and so forth. But main thing is that the conversion factors is going to be multiplied by the stopping powers, and this conversion factors with the perturbation, the factors should be taken into account. So these perturbation factors, as I mentioned earlier, is purely most likely coming from the detector side. So we actually this perturbation factors is kind of combinatorial factorization among various sources. For example, the effect from the replacing the water volume by the detector volume. So it's purely the volume effect of the detector, and also the non-water equivalent of the material in detector or. So it's a kind of material types dependence. And the other thing is the intrinsic differences between of the fluence between the water or detector side. So fluence actually basically difference, intrinsically difference between two mediums, or some structure-wise of the detectors, detector type, or contribution of the central electrode or stem or and other detector structures may play a role to determine the perturbation factor, one of the perturbation factor. So this is a kind of good example, which is the published the 2008 Wolf, the Monte Carlo simulations, and development of the Monte Carlo calculation for the perturbation correction factors. Here we see that how actually perturbation factors are going to be demonstrated as a possible perturbation factor calculations. For example, this is kind of idea, the pin type detector, the PDWs as in the 8708 or 8709 type of detector. So a chain of the dose ratio, which include the effect of the different chamber component, is going to be combinatorial this chain perturbation factor of the chain is going to be actually final perturbation correction factor. So for example, the D2 over D1 take into account these perturbation factors coming from the central electrode, and then the D3 over D2 in the factor from the stem, and D4 over D3 is coming from the word effect of the detector. Basically, overall D5 to the D4 or D1 is going to be overall combinatorial combination of these the perturbative factors to put into the conversion factor. So this one is an example of the Monte Carlo simulation, real Monte Carlo simulation, electrode in the center here, and by encapsulated by air outside, and the outside of the capsule there is a water mediums, which is here. So we can define this electrode, central electrode, and the air capsule is going to be defined by sensitive volume area, which called detector, meaning that the inside of the detector should have interaction process and tracking process, and take into account the correction in order to get the correct dose calculation. So this actually the representative of this last picture of this one. So that's why the insensitive area there we can have a lot of electron shower. You can see that inside of the volume. The other example is that the MCTP Monte Carlo treatment planning process under the CT image process is kind of well-known example, and there is a standard step to calculate the dose through this Monte Carlo simulation. And first one, as you see in the picture here, is determine that the phase-based data after the primary linear collimator. So once you see that the collimator we are using here, and then you can determine that what is the phase-based the beam distribution look like. Secondly, and as you see that the computed at the phase-based data, and you can define the size of the field, the beam, by applying to this collimator. So it's kind or multi-leaps kind of in and out, or determine the size of the field, and before the patient patient radiation. And lastly, they calculated the dose distribution for the particular the patient-specific the CT geometry, so we can actually use that the patient geometry and to determine the dose distributions. One issue or questions, the major question in terms of the molecular treatment planning systems, people argue that there's actually basically two arguments, because 1 and 3 is connected. So one is that the molecular treatment planning calculated should carry on by the dose to tissue or the dose to waters, and if so, and how accurate the conversion between these two calculations. The second one is the MCTP inherited calculated tissue dose accurately, or if so, and how much accurately you can trust. Well, there's a couple of studies has been going through. Here is the stopping power ratio, the tissue over water, and real tissue or the organs really depends upon the density, and also depends upon the ion pair energies. So I just see that here is the stopping power ratio is a function of energy of the electron. Most likely water's case is kind of flat and is unity, but depends upon density effect. Is the adipose tissue and the bone tissue is going to be different behavior compared to the water because different density. So this density effect is the function of energy dependence, and not only the density effect, but also like difference between the dashed curve and the solid curve, even the same adipose or bone, because of the ion pair, the values difference from the ICRU or ICRP, which is about the 15% of uncertainty. So those the report actually International Commission of the Radiation Unit report or International Commission on the Radiological Protection report is give us like slightly different answer about the I value. That actually depends upon the depends upon the energy dependence of the stopping power. Same thing is that here's the energy fluence, energy dependence of electron. As you see here, the electron fluence is in showing here that the red, the blue curve, and at the same time in the cumulative dose of fractions and in the right hand side, which is showing the red curve. As you see that this cumulative dose fractions is actually the about energy about the 7.75 MeV case, and we only have 50% contributions of the dose absorption. So mean that the calculation of the electron for these regions is not only contributed on the 50% of the dose, but also like another 50% dose is going to be lost. So contribution to the water by energy beams is going to be taken into account. So in that cases, for such a deviations argument is, a short answer is that the treatment planning system and the Monte Carlo treatment planning systems, and that calculation of the tissue dose is actually to the reference dose to the water. It should be obtained at the beam calibration, mean that we can use that the both tissue dose and the water dose is equivalently. And the second question is that how accurate of the tissue dose, and actually, as I mentioned earlier, there's a generic the ion pair energy values presented by two different reports. It's already give us a 15% of the certainty parallel, and this is kind of the major limitation of the MCTP, and even full Monte Carlo simulation. So individual body tissues stopping powers are required, and then in that the MCTP should take into account this intrinsic uncertainty. So under the some Alara or Alabaha conditions, this within enough statistics, and the MCTP already give us the accurate enough of those calculations on top of this intrinsic uncertainty. So this is still the kind of spurious the methodology compared to the other analytical algorithm calculation of the dose. Well, this is another example of the ICRP lung and soft tissue, muscle, or bone, adipose. For example, this is the perturbative the factor, correction factor, particularly the fluence correction factor. I just see that even the same lung cases, we have a different factor you have to apply, and even bone, the compact and the critical cases, do we have significant differences you can see. So finally, the stopping power ratio between water and tissue, and that should be taken into account the dose ratio between water and tissue, and multiplied by this fluence differences between the tissue and water, and then that kind of correction factor should be taken into account, and then we can expect the precise stopping power ratio and dose calculation. So this is another word that the dose calculation of water kind of correlated between the tissue under the Monte Carlo simulation is corrected by the fluence factors, and for the charged particle and the photon cases. So ICRU report 90 actually improved a lot, and also the summarized this research argument, and they conclude these two the answers from this report as well. And they talk about the Penelope and the EGS NRC and the FLUCA and GN4 MCMP. Those commercialized those calculation Monte Carlo basis, simulation basis calculation already take into account this detailed correction, the perturbative factors, and also the fluence differences take into account, and provided precise those calculations under the intrinsic uncertainty. So that's all about, and thank you so much for your attention, and let me know your suggestion and comment or any questions. So reference book is actually our textbook. Thank you.